segment of the flipped lecture, I would like to discuss some more interesting and, if you want, more complex example. The first one is when we find a problem which may have no solution. So basically, here I am studying a case in which I want to minimize a function, but actually there is no minimizer. That's exactly the same function that we have seen before, and in particular, so for example, this is my function. This is g. It's a function of x and y that we have already seen: minus x squared minus y squared plus x times y plus y. So if I want to find the minimizer of this function, I have, as you know, to define the b version of the function as a function of a unique variable. I define proper sequences for x and y, and I can plot a graph of the function. And you can easily see here, when I use persp, that this is a sort of hill, and it is intuitive that whatever is the initial point, wherever I place a ball on this surface, the ball is going to roll down to infinity, going down, and basically this is the intuition for which we do not have any minimizer, because the ball can roll down forever. But what's happening when I use R in such an example? So what's happening, for example, when I try to minimize a function typing optim, starting from the point 1, 1 of the function that I have previously defined. As you see, R is providing some output, and you may think that this is a minimizer, even though there are a lot of indications that this is really sort of fake minimizer for a variety of reasons. Let me start from the first. So if you look at the convergent part of the list produced by optim, you see that there is a 1. And as we know, the correct conclusion of the optimization algorithm should be signaled by a 0, which means that the minimization was successful. But in this case, we have a 1, which is pointing out that there are problems. Second, we can easily see that there are problems, because if you look at the solution, which is here, you should immediately realize that these are very strange numbers, because they are very large ones. So here, for example, you have 2.6 times 10 to plus 55. That's a very huge number. The same can be said for the y. And if you look at the value for the function at the minimizer, you see a negative 6 times 10 raised to power 110. So again, this is a very large negative number approaching minus infinity. And whenever you see such a solution, clearly this is pointing out that indeed R was unable to find a minimizer, but the ball was rolling down for a long time, and this is clearly not the solution you are probably looking for. Let me also spend some time on a more difficult problem. From an abstract point of view, this is again stressing the importance of picking the correct initial condition when you have a minimization or maximization problem. So consider, for example, the function that you see here. I mean, the function is not really important. What is important is that you can define the function in the standard way. F is a function of x and y. Then you can define the b version of this specific function. Here, again, it is very handy to have the chance to write the FB exploiting the previous definition of the function x, of the function f, and you can have a contour plot. As you see here in the contour plot, let me zoom on it a bit. As you see here, for example, you see that, that there are several local minimizers. So, and because you can clearly see that there are sort of circular areas inside which local minimizers are located. So one important problem here is to find the correct initial condition. So assume, for example, that we start from the point 0, 0, which is here. Well, we roughly speaking start from here, And as you see in the next slide, we indeed reach a minimizer. The minimizer is at the point 1.06, 1.06, at which your function is getting a value which is very close to 0.6. But if I start from another starting point, for example, if I start from -2, 2, I reach another local minimizer. In this case, x is -2.12 and y is 1.49. However, in this point, the value at the minimizer is 0.51, which is smaller than the previous 0.6. So basically, depending on the initial starting point, we reach the different solutions. And if you let me go back to the graph, I can try to show you what the previous graph on which I zoomed a bit, and I can try to show what's happening. So for example, if we start from the point 0, 0, which is about here where you see the cross, we were converging to this solution. So my algorithm was basically finding a local minimizer. It was going down my surface and reached this solution in which the function is actually taking a value which must be smaller than 0.8, and it was indeed 0.6. However, if I start from another initial condition, which was -2, 2, which is about here, you see that my algorithm is finding another solution, which is actually more attracting than the previous one, because it is inside an area and it is smaller than 0.6, and it actually turns out then it was 0.51, roughly speaking. So I hope this example is clearly showing that whenever you have a functions for multiple minimizers or maximizers, then the choice of a proper starting point is really critical, because depending on the point you will end up in different local minimizers. And for example, if you think that this may be the cost of running an enterprise, say, then you may end up in finding a minimum cost close to 0.6. This is indeed a local minimizer, but you can save another $90,000, say, if you find another minimizer with different parameters, because at the final point there, you only get a cost of $0.51 million. And if you find a similar situation, some careful inspection of graphs or other techniques are indeed needed to start the optimization algorithm from the correct starting point. Thank you.